guys, my name is Nina. I'm president for IEEE here at SF States. So if you guys do like having these workshops and want to see more, you guys can go ahead and join our officer team. We're going to be having our officer elections this upcoming May. The date is still to be determined, but we will post on our Instagram and our Discord. So these are our fellow officers as well. We have Firehouse Day and Robert Johnson. I stand for the exam.
My name is Dan, of course. I'm the grad student.
So I would like to thank Larry and Kevin as well. We've been working with them the last few semesters, and this is our first in-person workshop in almost 2 years. That is all.
Give a big round of applause. If I want to follow IEEE on Instagram, what's the Instagram handle?
Oh, try right now. It's IEEE SF States.
And then what major do I have to be to join IEEE?
So the major doesn't matter. Any major is fine. You have electrical, computer.
But does it cater mostly to electrical and computer?
It's mostly electrical and computer engineers, but we do have some computer science.
I see.
Officer, you guys can also join the publication. Instagram, so our Discord, we can.
It's on the right.
Yeah, our Discord on our Instagram. And if you guys have any other questions, you guys can ask the officers. Woo!
Hey, live people. Live. The first time I've been like in front of like a normal classroom in a really long time. So thanks for coming. I'm Larry from Intel. We have Kevin over here. Is everybody an EE major? So if I told you a few jokes about philosophy majors, I wouldn't be insulting anyone. Okay, so my stepson is going for his PhD in philosophy. And when we went to his graduation for undergrad, the dean told a couple jokes that I like to tell. So the first one is, how do you get a philosophy major off of your front porch? Pay for the pizza. And the other one is, what can a park bench do that a philosophy major can't? I sleep on it. Support a family. All right, you guys will have to see how you do. I have to come up with some better jokes, or maybe I have to find some EE jokes. So, pardon? Okay. So I'm Larry. I run our university outreach for the Intel division that does FPGAs. And I think my next slide talks about me. Yes. So I've been in the industry for a long time. That explains the wrinkles that are underneath my mask and the green hair. And I've done a bunch of different stuff in design, sales, marketing. Most of the time I've been in semiconductor companies. I used to be at a company that's now Broadcom for 15 years, and then been at Altera/Intel for 18 years. And I also teach. So the last semester I taught was at Sac State. So your counterparts over in Sacramento, I taught a grad class there last fall. And I taught at Santa Clara a couple years back, and Cal several decades back. I taught a basic class over there, and I'm California native. I went to CSUN myself, so another Cal State product. And you guys heard of LMU, Loyola Marymount, so small private college in LA. I like doing California type of things in my spare time. And just a little bit about my job. So I do a lot of workshops like this. I work with faculty a lot. I work a fair amount with Dr. Mahmoudi. So any of you guys take Dr. Mahmoudi? Maybe all of you. So really great prof. uses Intel FPGAs, yay. So work with profs about, answer questions about boards and curriculum, run workshops, we hire people. Yeah, so that's what I do. Fun job. Okay, so what we're going to talk about here is, I don't know how to get this little guy out of that screen. It's impossible. Is there a way to hide that? Window. Not sure how to do that in Zoom. I guess it just escape.
Or you can drag it around.
Oh, will it move, like slide it? Oh, maybe I'll just put it down here. How's that? But then I can't find the little slide thing. Let's try that. So now I lost my mouse. Where are you? There you are. But it turned into a pencil. How do I get it back? Now it wants to draw. I don't want to draw. Annotate. Where's annotate? F5. Not on this. Now I got more crap up here. All right, come on, stop. There it is. I think, no, and now it's trying to do something else. The red what? Where? That guy. Oh, thank you. All right. All right, that's a little better. All right, so maybe that won't block my slide so much. Thanks so much. That's why he makes a big box. I need to retire and let you guys come in next generation. All right, so we're going to talk a little bit about Moore's Law and a bunch of topics about the semiconductor industry, what it's like to work. We'll talk about the job market, then we'll talk about how to run the tools to do the lab. I'll probably yap for a little over an hour, so be patient with me. The good news, I see you face to face, so if you fall asleep, I'll know and I'll try to go faster. So let's start off with Moore's Law. So has everyone heard of Moore's Law? That's a yes. Cool. All right. So this guy founded Intel. Now he's up in his 90s and happily retired. And he wrote this magazine article that he drew this graph of the growth and the density of transistors that you can track in a given area over time. Right. So you guys heard about this. This is the actual kind of graph that he put in the magazine article in 1965. And it still kind of holds true today. So he speculated that the density of how much you could pack, and it said, I think this is, I'm seeing a trend, and amazingly, the trend is more or less continued, although sometimes it stretches out a little more than 24 months. But so what happens to sort of keep that cadence of technology growth is not only do you need the Intels and the TSMCs and all the semiconductor companies, but you need all the equipment companies and companies like Nikon that make the optics, and all the pieces need to come together. So they all kind of go, all right, we got this node nailed. Now we got to go to the next one. So these people, play nice and collaborate, and they come up with a new technology. So what does that mean in your world? I don't know if that's too tiny, but I'm sharing screen, so hopefully you can see it on your screen. So one example is iPhones, right? So the first iPhone was introduced in 2007, and you can see the screen size there was a 90 nanometer technology, and so on and so forth. And usually about every 2 to 3 nodes, every 2 to 3 models, there's a change in technology, right? So it jumps to 45 and 28, and the current iPhone 12 and 13 is in 5 minutes. Okay, so I don't know about you, but I've probably had, I kind of like get about every other model, I think, of iPhone. So I probably had 6 or 7. And I always forget to sell the old ones, so now they're all sitting in a drawer in my house somewhere. But maybe they'll go in a museum someday. But you can see the effect on Moore's law, right? Better camera quality, denser pixel packing. You know, the LCD display looks really nice. You got some AI features that kind of builds right into the phone, and so on and so forth. So that's kind of one example of how Moore's law plays out in your day-to-day life. And kind of a neat tidbit, over 1 trillion chips sold per year across the entire industry. So the good news about that is there's some good job prospects when you're selling that many chips. So what do we got? 7 billion people on the planet, something like that. So it's like 800 chips per human, something like that per year. It's like crazy. Another way to look at this is video games. And so here are some different consoles, what year they were introduced, and the feature size of the main silicon processing chip. So if you go back to the Nintendo and early Nintendo systems of 1983, which is probably well before all you guys were born, right? So the feature size was 600 nanometer with 3,500 transistors, and you can see the resolution per different console, right? So the first one, limited colors, 2D looking, very pixelated, no real concept of like shading and shadows. Starting to look better in 1998, giving it more of a 3D. Here, I mean, you can pretty much tell a skin versus, you know, leather or metal and the different types of textures. And then this is actually like Horizon. PlayStation 5 really almost can't tell the difference between if it's a person or it's a computer generated image, right? So as she rotates her face, the shadows, you know, where the light source, you can kind of see the light source looks like it's kind of above her. You can see the shadows. She was to look up, the shading would change, things like that. So amazing stuff. All the calculations made by lots of transistor packing. Let me see if I can show this video. So this is courtesy of my colleague Kevin. This. Cool. So lots of good use of transistors. And I'll see the, let's see here. Pardon? Screen sharing, so, resume share. All right, that working now? Should be, all right.
Yeah, that annotation, how do I shut that thing off?
You look to the button with the annotate on the top of the screen.
Why am I not seeing it?
It might be on the others.
Oh, here,
There it is.
here, this
Yeah.
annotate, just
Yep,
like
click
turn
on
that off.
And then there's a trash can. And there's clear all
Oh,
drawings.
clearing all fronts. There we
There you
go.
go.
All right, that was that little mark that was driving me crazy. So, all right.
Careful, I think you're still on, go just like over the mouse. Over there. There you go. Now you're safe. You won't draw anymore.
Ah, okay. I get rid of that thing. And then this thing wants to annoy me, or I'll just put them down here. All right. So the other thing besides Moore's law is this thing called Amdahl's law. And the idea is that you get more throughput with more processors, right? And you see that, I think this is 8 processors on my laptop. Anyone know how many processors they have on their laptop? How many cores? Yeah, how many cores?
6 cores.
6?
Yeah.
Okay. So yeah, laptops seem to be 4 to maybe 16. Desktops, maybe 32, 64. Servers kind of the same. You get to GPUs and there's a lot more cores, thousands. FPGAs that we work on, you kind of decide how many cores you're going to build, but custom build. But at some point, you don't have enough I/O to get all of the data in, and you don't have like enough. You just can't get access to memory. So Amdahl kind of came up with this theory about how much throughput you get. This thing moves. And there's a lot of neat products out there, like the modern GPUs really look at Amdahl's law and try to take it to the limit in terms of how much parallel processing. But imagine if you made a 50,000 GPU core, you probably wouldn't be able to actually get the data in and out of it. So it would kind of happen. But lots of neat stuff, especially for AI. So a lot of people are saying we're in the new era of architectural innovation, and it's because of these parallel processing capability. Now this. All right, I'm going to go through. You guys all know how transistors work, right? We got a lot of stuff to go through, so we'll go through that. Couple examples of how small 14 nanometer is, so a little bit smaller than a coronavirus. At iPhone 12, iPhone 13, we said was 5 nanometer. So the drawn gate length is only 20 silicon atoms wide, which is just nuts. I don't know how we do it. I like to take credit for it. Yes.
They kind of changed how they measure that now.
They kind of fiddle with if it's sort of the effective, but it's still narrow. Whether it's 20 or 30, it's still crazy small. And so we do know that at some point, like Moore's law, the ability to sort of build the normal CMOS will come to an end. But it's probably a good 15, 20 years out. Doesn't mean we're going to stop, coming up with new innovation, but at some point you can't go narrower than a single silicon atom. There's another kind of neat, see if I get this to work. I'll tell you what, let's keep going just in the interest of time. So other comparisons of the drawn feature size is at 7 nanometer, I can fit 10,000 drawn gates in the width of a human hair. It's pretty nuts. And then this is a picture. If you cut into a silicon wafer, you can see these are the different metal structures. So these little things kind of look like teeth or vias, so they connect the layers above and below. And you're looking at vertical and horizontal wiring. I don't know how many layers that is, probably over 10, but that's pretty typical on a modern semiconductor to have that many layers. Real quick, and do you guys study how wafers are built? I'm gonna put a video up here for homework if you ever want to know. This is absolutely the best explanation of how silicon wafers are built. Just Google this thing called Silicon Run. It's about 35 minutes with really nice graphics. and it's really old. It was, I think the video was 1995. So all the cool gadgets and stuff, you're just going, God, that's old. You know, that's in the trunk drawer now in my parents' garage. But it's a very well done video that was funded by, I think, the National Science Foundation and Intel and a bunch of semiconductor companies. So I recommend looking at the video. Basic idea, you start with a large ingot of molten sand, basically a pure silicon ingot. You cut it up and grind it to be very flat. You form an oxide film by annealing and heating up the wafer. And then often people ask me why wafers are round, because you kind of cut off the edges and die. One is you spin it really fast with photoresist, and it probably get kind of wobbly if it was square. So I think that's one reason why it's round. So you basically, you know, put a pattern, and then when you hit light, that part of the photoresist will etch away, and the other part will stay. And then you kind of go through this mask making step. So this photo mask is super expensive. These things are like, for a modern like 5 nanometer semiconductors, some of the masks can be over $100,000 just for one mask. So you don't want to screw up, like don't make any mistakes. But then you put the pattern here, and then this is kind of like a stage that moves around, and it builds the different die patterns, and then you go through this process over and over. So you go in and you put an image, and you do some sort of etching, and then move to the next step and continue on.
The mask reusable?
Pardon me?
Is the mask reusable?
So what?
Can you reuse the mask?
You can use the photo mask, so that's a really good question. Let's say you build an x86 processor, like Intel or mainline processors that go in laptops. So you would take that mask set, and it's probably about 60 to 70 masks. And when you say reusable, use it over and over again as long as you don't damage and pattern, thousands and thousands of wafers, as many as possible. And sometimes you make multiple sets so that you can run high volume products. But the other thing that you can do is a technology called a structured array, which what you do is you take, say, the 70 layers, and 66 of them might be common for everyone, and then just some of the metal layers are customized. And so what you kind of do is use the vias to make the transistor do different things, but all the other stuff stays the same. Okay, so what a lot of companies, it's kind of a boutique ASIC product, like it's not in the highest of volume. But I worked on these things for a long time at my previous job at Logic, and also when I joined Altera, where we use these gate array type of products that only use 4 layers. So it's like, it's not the highest volume. It's kind of in between an FPGA and a full-blown custom chip. So that's how you use it. Okay. Okay, so then you develop and you etch out and you start building these different features, and you etch, and then you implant different type of chemicals, and then you start applying wire and etch away wire structures, and then finally you have what, it doesn't show the final top layer, but there's a top layer that's like what they call passivation, which is a glass. You want to encapsulate the die so that you don't get any contamination. So that's it. And then you chop it up, and first you actually test it, you figure out which ones work, and then you should put a deep spot on the ones that are bad and the ones that are good, you pull off and put it into a package. Okay. And then you stick them in a package. I didn't bring my props. Sorry, I had a bunch of packages I could have shown. But this is one way, is you basically you put the die in the middle here, and it's almost like a little gold wire soldering machine, almost like a sewing machine, actually,
attaches the die to the lead frame. And then you encapsulate that in epoxy. So most of the chips that you'll see, the lower cost chips, there's usually like an epoxy, black epoxy plastic. The more expensive ones, it's a metal pack because you want to draw the heat away from it. And then you cut this off, and then you put it on the board, and you heat up the board, and it solders. It's not someone individually soldering. There's something called wave soldering, sort of like spray solder that only sticks on the metal. Okay. Yeah.
This is the stuff where you guys would have some IHS.
Pardon me?
So like you said, like, and some of them would be IHS instead of epoxy.
Yeah, I mean, it's epoxy. There's a metal. Sometimes you put metal with the heat sink on it. It's all about. Sometimes it's ceramic. Kind of depends on like what. Ceramic is good for like space. It's a little more immune to alpha particles. Metal's good for the heat. Plastic's cheap. So it kind of depends what you're trying to do. And a lot of times, I don't know if you've ever seen a bulb array, but a lot of this has kind of the leads coming out of the edge, but a lot of them, if you sort of look at the bottom of a package, you would see something with these little solder balls. And if you look here, it would be the whole grid of these. So you put this on a PCB and you heat it up, and then the balls melt, and that's the way most somewhat complex chips are done nowadays with hardware. And then you complete it, make a bunch of money. So again, Silicon Run. Look at that. Okay. So now how does Intel and other semiconductor companies afford to pay you the big bucks? So, how do we make money, right? Every business is really here for, most businesses are around to make money. So the first thing to know is gross die per wafer versus net die per wafer. So let's say this is an AMD wafer, and that's an x86 processor. And this is the Intel wafer with the same class of x86 processor. Who's going to make more money, AMD or Intel? Yeah.
Would be backwards from right there because AMD is using a chiplet design right now. So, but if this was the two ones, then it depends on how much transistors are in each.
Yeah, I mean, basically, the point is if you have fairly equivalent functionality, if you can pack, the same function in a small area, you can. Okay, so one of the most important things is to make a good, concise RTL design that works, that uses, a minimal amount of transistors for the function, uses small process geometry, do a good job with the layout so that you can pack it in a program. Okay, so that's called gross die. But then net die is, there's going to be defects, right? When you're messing around with 20 atom-wide features, you are going to get dust, dandruff, coronavirus particles that land on your partially fabricated wafer and destroy it. So then it knocks out some of the useful. So that becomes your net die. Okay. So you can look at how the yield changes based on the same defect pattern. On this is 118 die. If we just said, okay, let's say I had double the number of die, you sort of are better off also making small die. So you can imagine, I'm just trying to make 4 die, I probably never use it. Okay. The biggest die that we make is about 25 millimeters on the side, which is probably about that big. Okay, and a wafer is probably big. But that's a really big die. Like that's like you probably put 20 billion transistors, but the yield's really bad. So unless you have some sort of means to like deal with some level of error and correct it, you probably won't get anything. The sweet spot, and I'll show you in a minute, is around under 100 millimeters, so probably about that.
That's like a good size for like a high volume, like mobile phone or laptop. You're kind of shooting for stuff like that because it kind of keeps the price, you know, like several $100. These things end up being like, you know, close to $1,000 per chip because it's just really hard to get a perfect wafer. You never get a perfect wafer. Okay, so we're driving towards the cost of the transistor to continually go down, right? So fine, here's the millimeter squared per transistor. All good, right? Follow Moore's law. Cost per millimeter squared going up. Why? Because it takes more atoms to make this smaller die, and you have to buy more and more expensive equipment to manufacture these things. But the net effect is as long as this is going down to the right, Moore's law lives on. If that has an inflection point, the economics get messy, and there's less imperative for companies to go in and go to the next technology. Here is at the Apple main processing unit die. So it shows the chip area. So the 16 nanometer is pretty large, 25. Not really what you want, you know, the gross die per wafer, not really as high as what we have over here. So generally it's a little under a centimeter per side, and at the end of the day, it continues to go down. Not much, right? Between 5 nanometer and what we expect at 3 nanometer, but it is going. Okay. So a lot of energy goes into this between Samsung, Intel, and TSMC, which is the three main people making the most modern. So yeah. Just the individual, like if this is a wafer, right, and it's cut up, a die is just one single like chip, a die or chip. Okay. All right. So lots of people and companies like Intel study these charts to the nth degree to try to figure out the economics of it. Okay, so if you're ever interested in this sort of thing, you know, supply chain management, logistics, certain marketing roles, that's for you. Okay, you can take your EE degree, but use it more for business application. Okay, one of the takeaways is when you're sitting here and you're taking all these courses at SF State, and you graduate, everyone kind of thinks, oh, I'm going to be a designer. I'm going to just like be writing RTO code, or I'm going to do chip layouts or designing transistors, connecting them up and running SPICE. Nah, that's like some of it. There's a bunch of other stuff, right? You got to think. There's a lot of people that have to think about this. People that have to market it, to go to like CES trade shows and, you know, wow the audiences. But everyone's using their double E degree to do all these different type of roles. Okay, which is great. So you have a lot of different options in terms of what you want to do with your career. Okay, so to kind of summarize the things that we think about all the time at Intel, we want to make profitable wafers, right? The wafers in a given node, like a super modern node, like probably like $10,000 a wafer, okay? And you're trying to make sure that you make little tiny die, right? So you can sell a lot of them. You know, you want 10,000 die per wafer or something, and you can make tons of money off this stuff, right? If it ends up being a really big die, it's harder to make money. So want to make a lot of profit per wafer. You want to have the highest performance, lowest power, and this one's really big. Okay, when you put 20 billion transistors on one single chip, it's really easy to screw up. It's incredibly easy to screw up. It's a lot of information. It's very difficult for design management to try to think about all the things that go wrong and build working silicon. Okay, and because of that, you don't see that many silicon startups. There's a lot of consolidations. When new companies come up, you kind of need a certain mass and scale to get where you can build reliable silicon. So late 90s, there were startups all over Silicon Valley, so chip companies. But a lot of them went under, some of them got bought. Now you're actually seeing some consolidation. We'll talk about that. But it's really, a lot of it is to try to offset. You need a big enough scale to avoid mistakes. Okay. So yeah, 5 nanometer single wafer, $12,000. $10 million for the asset. It's not for the faint, not faint of heart. Like this is it's a fascinating business, high risk business, takes a lot of capital. And you definitely want to, be very precise in the work. Okay, I'll go through this. I'm going to skip this and we'll go through this in a moment because I've got slides in the other section. So bear with me. All right, just to kind of finish out the semiconductor overview. Okay, so this is kind of the impact of the job market, right? I just kind of picked up some various interesting facts that I thought were interesting. One is EE job growth rate. So right now the job growth rate is 6.7% year on year. So that means that old guys like me are starting to retire. That means that you guys are coming in and replacing me, and still there's growth. The number of new grads aren't really keeping up with that growth, which is elevating wages, which is good for EEs, probably bad for consumers because it makes the price of things go up. But you picked a good major. 277,000 U.S. jobs in EE, and let's see what else is interesting. So then you have indirect, right? So this is just semiconductor, but then you get like the equipment manufacturers and software companies and such that are supporting this part grows to 670,000. And then when you add like enthused, this is like you make good money as a EE and you go off and buy a nice dinner, so you're supporting the restaurant business, or there's a concrete company that's pouring the foundation for a new fab, right? That's that thing. So employs a lot of people. Good thing there. And then this shows the state. So we're in the highest level of employment is California. In terms of the numbers that are in semiconductor. Although if you did it by per capita, it kind of looks like Oregon's the best place to be. Like if you were to walk down the street and bump into someone, you'd have the highest probability that, there would be a higher probability that they would be an EE than if you ran into someone randomly and said, "Are you electrical engineer?" In other states. But great place to be. You're in right in the heart of where it's all happening. Kind of looking at revenue, been going up and to the right. Things happen that we can't predict. Asian financial crisis was something at the beginning of the 2000s. Then you might have heard about the dot-com bust. I'm sure you heard about your parents grumbling about the recession in 07, 08. Then you get these are kind of macro level. This is for, specific to the industry. Anyone have an idea why the PC and DRAM slump happened in 2012?
Well, that was around the time when they started to hit the problems with the shrinkage of the node sizing, where the atoms were skipping panels of things. Right?
That's why. But there's also kind of a usage. Think about how were people getting their internet in 2012 versus maybe 2005.
We had to build a lot more infrastructure for mobile networks.
It's all those mobile phones, right? So now you're spending a little bit less on your mobile phone. It has a little bit less semiconductor content than your PC, and it's doing for the average person, they're getting all their internet consumption through the phone. So it took a hit on the PC and DRAM, but then things start picking up again. Then everyone's getting in the business of memory because the prices are going up. So everyone starts opening up new fabs, and the price is the same. And it kept like Samsung and Micron had a really bad time around 2018, but they priced themselves. Now things are looking pretty promising.
The biggest catalyst for growth in computers for like a really long time, basically.
Is what now?
COVID, like the pandemic was a big
Yeah. Yeah, send all your kids home and tell them to buy a PC or they can't go to school. Yay for Intel. AMD, a lot of companies, you know, go buy video games, go buy lots of TVs because you're gonna be home for a long time. Okay, a few other topics and then we'll move to kind of more about our FPGA lab. So have you guys heard of, like, you know what a chip fab, we call it a chip fabrication facility, it's called a fab, right? In the beginning of time, if you started kind of like automobiles, there's not too many automobile companies that outsource. They design a car and then they send the car to some other factory. You just make your own factory. Not true with chips because they're just too expensive. So in the beginning, everyone was like Intel. You had all these big fabrication facilities, but most companies now, there's very few that actually have their own manufacturing. Intel's one, TI's got some fabs, but companies that you hear about all the time, AMD, NVIDIA, Qualcomm, Broadcom, none of them have any factories. Okay, so that's called a fabless. That means they have to go and outsource the manufacturing to somewhere else. And the one that you hear about all the time, everyone here, TSMC, Taiwan Semiconductor, right? Yeah, Taiwan Semiconductor. So they're kind of the really doing well right now. They're based in Taiwan. You can see more and more companies are moving towards the fabless model. I think the last one I heard was like maybe 33% or something like that. Okay, and only 3 companies are keeping up with Moore's law. Everyone else kind of like said it's too much money to spend. We can't buy all the equipment. We don't have all of the PhDs and stuff to make 20 atom-wide transistors. So these 3 companies are the only ones big enough to do this. Yes.
Also, you know how during the pandemic there was a lot of demand for car chips and such.
Yeah.
Right? As far as I'm understanding, there's still like a lot of other niches besides like the highest end kind of gaming stuff or for servers or whatever, where we need older nodes for making like simpler things, right?
Yeah. The car thing kind of happened because, you saw the pictures. It was like fascinating to see San Francisco with no cars in the street. It takes a long time from the time that you place an order to the time you get your chip. And in normal times, it's like 6 months to build. From the time you place your order, it gets placed, it gets scheduled, you got all these steps, sometimes it has to bake for a couple days, it's a lot of work. So all the car manufacturers said, we're not gonna be selling any cars towards the end of the year. I think we'll just like hold off on our orders. And then suddenly all those orders started getting, the fab started filling up with other stuff. And then things started coming back because COVID looked like, all right, well, I guess it's getting better. I'll go buy a car. Well, there's no chips to put in the car. And then you compound that with like shutting down the port of Shanghai for 2 weeks, and no one's loading things up on shipping containers, and it's just this ripple effect. So yeah, there's a lot of logistics and a lot of different parts to making a chip, and so that they're still suffering. We're expanding a bunch. Here's some kind of headlines of different things that have happened with Intel. So big $20 billion plan, can employ thousands of people. Maybe you heard about this Ohio factory. Did anyone watch the State of the Union? Our State of the Union presidential speech, our CEO kept on showing up. It was cool. Like, hey, there's Pat Tails for CEOs. So obviously excited about big expansion of U.S. manufacturing. We bought someone. We're going to do a big fab in Germany with like other research centers. There's a lot of stuff going on with manufacturing and Intel. And then some other kind of pieces of this business is the semi-equipment manufacturers. So the U.S. ones in this list are Applied Materials and Lam, and they're based in Silicon Valley. So when you're job hunting, of course you need to go and look at Intel, but look at these guys too. It's not something you think about or maybe you hear in your classes, but lots of great high-paying jobs and applied materials and Lam Research right here in Silicon Valley. Tokyo Electronic, obviously in Japan, ASML is in the Netherlands, KLA is Japanese, and so on and so forth. You can see a lot of Japanese sound companies for this, but this is a really, you guys ever heard this term CAGR, C-A-G-R, compounded annual growth rate? Whatever you're doing when you're job hunting, like study the industry and look at the growth rate, okay? You want this thing to be a positive number, and the more positive the better. It means there's a higher chance that you'll grow with the company will grow quickly. And the semiconductor industry last year was 550 billion. This is 62 billion, still a pretty substantial amount of money, employees, lots and lots of people. So this is a good place to kind of think about for job hunting. IP, everyone's probably heard of ARM, right? So that's the company that sells design, and then you integrate that design into your own chip. So everybody's using ARM for mobile, total domination in that particular market. And IP is kind of, all the library functions that you can put into silicon, and EDA is the CAD software for building electronics, dominated by these three companies. Okay, where are these guys headquartered? Anyone know? Mountain View. Where's this one headquartered? North San Jose. And Mentor, Wilsonville, Oregon. Okay, so these are great companies to work for. Synopsys, Cadence, Mentor, high paying, pretty interesting work. A lot of coding. Obviously, they need a lot of software people, but they need a lot of hardware people. So that's double E's. These are also good places to work. They're rumored to pay really well, and they have a positive growth rate. So things are looking pretty good in there. Yeah.
So those are the companies that make the software that you guys use to design chip design?
Right. Right. So a big company like Intel, we write some of our own software. If we can't buy it. It used to be that Intel's like, oh, we'll just do everything ourselves, right? But as time goes on, these companies are getting more and more credible, and now we buy most of our CAD software from these three or other related companies. Okay, and then just to kind of end off, just a couple of kind of headlines that we've kind of touched upon. So, chip shortages, right? We're all hearing about it. Inflation, lots of challenges there. Ford shutting down their assembly line because they can't get enough chips for the F-150 fast stuff, right? And this is really important to know. Asian countries produce more than 70% of global semiconductors. And the US government wants to change this. This is a security threat to the US. If China, God forbid, got greedy and started doing what Russia is doing to Ukraine, if they went after TSMC, our world would get turned upside down. So, hopefully the world won't get any crazier than it already is. But the US is, I don't know if it's signed off or it's really close to getting signed off a $50 billion funding to help out US semiconductors. Okay. So most of manufacturing is really based in Taiwan, South Korea, China, and again, lots. So that's creating jobs for the US. Yeah.
I think that's interesting what you said. Maybe Ukraine, I thought about that, the thing with TSMC. It seems like if Taiwan was to get invaded because TSMC basically is so integrated into the world economy, wouldn't it seem like you just wouldn't let that happen? Because if TSMC had to shut down production, that would pretty much that would be like the biggest stock crash ever, right?
It'd be hairy. It'd be hairy. Yeah. I'd be selling everything in sight and putting it under my pillow if that happened. But, Ukraine makes some stuff that's important also to the supply chain, neon and things like that, but nothing quite as, TSMC line shut down or, we put sanctions on it, that would be pretty scary. I'm not going to go into this in great detail, but beyond more, this is kind of a topic that comes up of what happens when we can't shrink the silicon smaller, but kind of three vectors. So different methods of making silicon, new types of computation like neuromorphic quantum computing, and then new architecture. So those are kind of the three thrusts. Lots of jobs in semiconductors are thinking about how to move to the next node. If you ever do master's PhD work, it's highly likely that you'll be involved in some of those vectors. So to kind of summarize, last year and this year, chip shortages are still dominating. Every year is just awesome mobile products, right? Just getting smaller and tinier things, always great phones. A lot of stuff with chiplets. Intel's really good at this. We're kind of the leader in integrating multiple chips together, either stacking them up vertically side by side with really high bandwidth. We have a new CEO with definitely a an aggressive vision for expanding our manufacturing. You guys probably heard of Xilinx, our competitor of Intel for FPGAs, and these guys merged and it just closed out 2 months ago. And NVIDIA tried to acquire ARM, but it didn't go through. Okay, it was a lot of countries kind of complaining that might create some sort of monopoly, so it never happened. All right, so maybe a little bit about job hunting. So Intel it's either us or Samsung, and we kind of trade places every once in a while, but we have 121,000 employees. I took some statistics on, just looked at this earlier today. So okay, so Intel, in terms of jobs, you can find out this data easily, but we have 5,800 job openings. Okay. And this has 121K employees. NVIDIA job openings was 3,540. Highly like crazy. AMD has 15.5K employees, and job openings was 2,164. Just for an example. That's pretty amazing. Like, this hasn't happened. When I started my career, which was back in 1985, the market was pretty hot, but it's pretty hot right now. Okay, so doesn't mean you're going to instantly just get a degree and get a job. You still have to work for it. You have to have the right skills. These are some of the hot things to have on your resume. When you're writing your resume, guys like me that do recruiting, you get 5 seconds to catch my attention with these things. Okay, so put your name, right, and contact information, maybe LinkedIn, etc., maybe GitHub, right? For me, when I do college recruiting, I want to know if you're looking for an intern or full time, and then I want to see those skills. Okay, I know Verilog, I know Python. Blah, blah, blah. Okay. Catch my attention really quick. Tell me what you're looking for. Okay. This intern or full-time objective doesn't need to be less than like a half a sentence. I am seeking for an internship of the summer of 2022 in the field of digital electronics. Perfect. You don't have to tell me your life story in that sentence. Right below it, tell me your key skills. Okay. Catch my attention, so then I'll read for more than 5 seconds. I can see all this stuff in 5 seconds. If it doesn't have that, next. Okay. Next thing is probably education. What's your major? More details. GPA. My kind of thing about GPA is basically probably 3.2 listed is kind of my cutoff. If it's less than 3.0, you know, but you're better in the major, you know, you could say 3.3 in major, something like that. Okay. Don't lie, but you can selectively use data, right?
Just on that, real quick, so you all know, my state FPGA, 3.3, but my overall FPGA got sick, filled out, got some state really, was a 2.7. This is your job, my last 60 units, I had all these.
Yeah.
This is always good.
Yep. Another thing, hand your resume to 5 of your friends and have them say, poke holes in this thing, okay? It better be 1 page. Keep it 1 page. Don't make it more than 1 page. Even me, if I'm job hunting, it's 1 page, okay? You know, if you can't, you should be able in 50 sentences or less, you can catch someone's attention and catch their eyes, okay? But have 5 friends look at it. Maybe you sit down, you know, over some beers or something, and everyone exchange it, and then exchange it or something, and have others look at your resume and find typos, find grammar problems, say, I spent 5 seconds looking at your resume and I still don't really know what skills you have, right? Try to look at those things. There's tons of, you know, you have a career center, I'm sure people come in and tell you how to write resumes. There's not exactly a right or wrong way, but that 5-second rule is pretty important for me. I do about 50 30-minute interviews with college grads a year, at least. So, and I've been doing this for like 5 or 6 years. So I've interviewed many students. Okay. Question?
How important is the GIT?
Which test? Seeing that I didn't know what it stood for, not very. At least not for me at Intel. I mean, I don't want to put it down. It's just not something that we typically look at. Yes.
Does GPA matter for the first job out of college or a lot of the first few jobs?
I mean, with me, you know, I'm close to 60. No one's caring about my GPA, but for you, you need stuff that differentiates you from others, right? And this is the challenge with, you know, what I'm going to look at is what school. And I've got something in my mind that, you know, if I see MIT, right, you know, there's like 4 or 5, like, okay, MIT, Caltech, right, just like the off the charts, awesome universities. No one's going to doubt that. Harvard. So you got that. Then you're going to kind of like, if you do a lot of recruiting, you kind of, you know, I kind of know what schools generally have been producing the best FPGA designers. But I'm going to look at GPA, and I'm going to look at skills. Right, and then I'll just know. I'm pretty good at, you know, and I think most people that do a lot of recruiting are pretty good at figuring out if you're the real deal, if you're, you know, just don't talk. Yeah.
Couple of things. So briefly, what would your like overall impression be of recruiting people for SFC? And do you need a graduate degree to work in semiconductor manufacturing?
I would say if you want to be like you know, designing the next process node, that would really help. You know, if you want to work on, you know, 3 nanometer, 18 angstrom or something like that, yeah, you probably need a master's or PhD. If you want to be like applications supporting people doing chips, you know, verification of Verilog, bachelor's is pretty good. You probably, you know, you might find a job, you get a master's, it's going to up your, you know. That's my recommendation for most people. If you're struggling job hunting with the bachelor's, just keep going on to a master's and keep looking at the same time.
I'm a MECI student, but in like the second half of my education, I've gotten really into all this stuff pretty much.
And you need to somehow get the skills high enough in there so that we can find it.
There's like a good portfolio helpful for that.
You got a GitHub with some interesting projects that might catch some attention. I personally like GitHub. I don't care about your code. I just want to know what projects you worked on. But if you sort of made some cool robot with mechanical and electrical, that would catch my attention. Other questions? Happy to answer them. This wasn't really like, I do have like a resume writing workshop that I've given here a number of times, but those are kind of my, you know, I think top things. How you get is who's graduating by perchance? Anyone graduating anyone graduating so in the spring? Are you out there job hunting? You don't have to say whether you got a job or not, but hopefully you're at least finding a lot of job openings and such.
No, it really isn't. I'm working at Peaceful right now because I couldn't get any kind of internship.
Yeah, you might. You're challenged with a different major, right? The further removed you are from EE, it's harder. Mechanical engineering, like Silicon Valley has some, right? You might find stuff at Tesla and stuff like that, but you might have to go to the Midwest where there's just a lot more mechanical engineering. But me as a recruiter, right, I'm going to go and say, okay, you got all these AutoCAD things, and maybe there's some Python and Perl. I'm going to, that's kind of cool, but okay, they're mechy, and I probably won't. To be perfectly honest, you know, that's kind of. Yeah, I would go through that really closely, and I would go through like finding an analyst report for people that are, you know, try applied materials. You ever look there? Right? You might want to try people that have a more mechanical nature, you know, try to find out that size. There's, you know, obviously you got the auto guys, Tesla being pretty big. I think NIO's got a pretty good presence. That's that Chinese electric car manufacturers. They got a pretty good sized office in Silicon Valley. And then also some of the medical devices, there's a fair amount of mechanical engineering that goes to that. Yep. So if you're mechanical, this is another place you might look at packaging. Try to find packaging jobs. Okay, because like I've worked with a lot of mechanical engineers that design the semiconductor packages. That's kind of a pretty cool intersection of like sort of analog and mechanical.
So that's like the LGA.
You know, you got your FPGA and yeah, all these, you know, different type of packages. You have to have good, you know, signal integrity. It needs to be thermally correct. It needs to be stiff and not bending, and you know, if your board flexes and it pops off, stuff like that.
Like 30%.
Yeah, that's
why everybody's buying LGA now.
yeah. Exactly. Any other questions? All right. So, how long have I been rambling? Yeah, a bit of time. All right. I want to get you started on the lab, so we'll move. Do I have anything else here? I think that's it. Okay. So we're at jobs.intel.com, and other companies might use something, but just go to it, right? So start with, you know, if you're interested in semis, just make a list of all the semi companies and start drilling through their site. Then start going through, you know, the EDA, Cadence Synopsys, Mentor, the equipment manufacturers. Then you might start moving over to medical devices and just start exploring all of the different places that you can find employment. All right. All right, let's start here. So this is today's lab. Kevin, you want to talk about yourself for a second?
So I have an application engineer. I'm going to be programmable solutions group in itself. I have a bachelor's in computer science, so they naturally dumped me in an ERTL. I was an education and training manager for the Air Force for almost 10 years. Got a large education background, so like talking to people is not making them used to. Really, you know, going through this program, I'm also part of the rotation program. So it's a program designed for new college graduates. I go through an 18-month rotation where I can pick 3 or 4 different rotations and work with different groups to figure out where I really fit in at Intel. So I can make sure that I'm happy for it, because that's the big thing is Intel cares about the people. Happy people are more productive. So right now, I'm working with Larry for about the next 5 months or so. I've been with him for a couple months now. I'm doing outreach like this, learning some more TL design, designing labs, things like that, and then I'll move on to another rotation. And then eventually, we'll be deployed to a full-time rotation.
Jeff, you want to stand up a minute and tell about your adventures with us?
I'm Jeff. I graduated 2 years ago. My bachelor's here at SFSU in computer engineering, currently got my master's in electrical computer systems. I met Larry through working for the university over at the FPGA lab. Worked with him for about a year now, March. Yeah, you know, I academic outreach and stuff. I write curriculum, I write bachelor thing for some of our servers, a lot of kind of stuff. So.
Okay. So yeah, we do hire SF State. I like SF State. I think you have a good program. Jeff's a really smart guy. You guys know Tyler Sheaves? Anyone ever work with him? You know Tyler? So he's interning with us for quite a while. He's working on his PhD at Davis. We have Anthony Anguiano. He might have predated you. I'm trying to think of anyone else. Okay. So yeah, I mean, I actually, people ask me about SF State. I didn't know much about the program. When I think about Cal State's programs that have like really good EE, Cal Poly is kind of the one that comes to mind. It's the hardest to get into, and it's probably it's pretty dang good. And I'd say SF State, Sac State are probably just a notch below it. And I'm going to kind of hammer on my alma mater because I've been back there a few times. Cal State University of Northridge is kind of a further step. Oh, I put San Jose State up here with SF State as well. So, pardon?
That's in San Jose State's definitely better. We don't even have a science.
Hey, no one has it going. We're sitting at home on Zoom meetings. So. All right, so we're going to go. Pardon me? Pomona's kind of in the mix there. They're pretty good. I talked to a couple profs. They have a pretty good program. It's not. Cal Poly Slow and Pomona are kind of at a different tier. But that being said, I also work with a lot of the UCs, and I think SF State's as good as half the UCs out there as well. It's all about having good profs. Like Mahmoodi's awesome. He teaches you all the right stuff. He gives you all the right skills to get in. It's really about profs. That's more than anything else when it comes down to it. The other thing, another thing about job hunting. Go to especially now that COVID's over, go to office hours, okay? Go get to know your profs, okay? Because if I get a resume and it says SF State, I might just shoot a note over to Mahmoodi and say, hey, you know this person? And would you recommend them? And they'll look up and go, oh, wow, they aced my class, but I don't know. I had that just the other day from a prof at University of Florida. It was like an awesome, I interviewed the candidate. I think they were great. And I recommend that we hire them. But my favorite prof over there who he took didn't know him. And that's a missed opportunity. So get to know your profs. Someone like me might ask a prof. You can also ask them if you're job hunting. Because we're talking to profs. A lot of people in the industry are talking to profs all the time. They're going to know where the jobs are. I usually reach out several times a year to profs asking, tell me your top students. And you're going to be, I will never miss the opportunity to interview a student that's recommended to me by a prof. I mean, they spend 30 hours lecturing to you, seeing, what sort of questions you ask. They're grading your projects, they're grading your papers. They're going to know a lot more than I can figure out in 30 minutes. All right, skip this because it's not virtual. Try to go quick. Already talked about that. Talked about just stuff we teach. Going. All right. So FPGAs. Has everyone programmed an FPGA before? Everyone take the logic design course? Taking it right now. Okay, who's teaching it? What prof? What's the last name? Okay, I've heard the name, I don't know. Yeah, okay. Yeah. And he uses Intel or Xilinx? Intel, cool. All right, so we're a 4,000 person division of Intel that makes these reprogrammable things, and this is small to large size. So this is, you know, like 20 billion transistors. This is probably 10 million or something. But they're programmable, right? You write Verilog or VHDL generally to program them, and you can keep changing the function. So you don't have to do all the manufacturing steps. That's why they're great in school, because you can try out all these different things. So flexible, because you don't have to do manufacturing, they're quicker to market. And we're like really big in things like 5G. So if you look at a cell tower, a lot of the newer cell towers are putting up the equipment for the 5G network. And that equipment has a lot of FPGAs in it. Why? Because the algorithms are changing. They're dialing in the network. Someone at Ericsson in Stockholm can, you know, reprogram a 5G base station in the Sahara Desert just by writing some more, you know, RTO code and synthesizing it, sending it through, and updating the hardware. Okay, so once the 5G starts sort of getting stabilized for, which is probably about 5 years, the new base stations that'll come out, Ericsson and Nokia will go off and build a custom ASIC chip because they're cheaper, like considerably cheaper. But you can only do that when you know what the function is in the something. So that's where, you know, Intel and Xilinx makes a lot of money, is in 5G data center. There's some distance competitors that kind of play in the lower end of FPGAs, the smaller ones, so like radiation hard or super low power. But most of it's dominated by Intel and Xilinx. Okay. So they're great for prototyping. They're great for learning how to be a chip designer. Lots of different markets. They're built with these things called lookup tables. If you took that logic design course, maybe they talked about how these things work, but basically you write, you know, some function, and I can build any function of 4 inputs with this structure. And the way I do that is I program these zeros and ones into memory. And then if I were to trace, you know, the midterm, what do I got? A bar, B, C bar, D, A bar, C bar, D. So right there. Okay. So that's this line. Okay. And you can work it out. You can do a K-map or something and reduce it, but that's basically how these things work. So the compiler goes in and just gobbles up all that code that you wrote. And first it makes sure that the syntax is good. And then it breaks it into these lookup tables. And then they get all connected together. Okay. What? Those are multiplexers. Yeah. So, okay. So one thing you'll notice is, let's say all I had was this path. So if I put all zeros in a 1 right here, what function would that be? Every bit of memory is 0 except the one in the far right. What function have I just made? Nope. What? If I had all zeros here and I want 4 instruments here, no. If I put a 1, my new interim question. So if I put a 1 here, right, and I'll have these 4 inputs, right? A, B, C, and D. This is a select. Those are the inputs, 0 and 1. And gate, yes. Very good. So they're all 1s. So A, B, C, and D are all 1s. This guy would be a 1 and everything else is 0. Okay? So what do we realize? This is a big freaking waste of transistors, right? So you know, but it tries to be smart about how it packs in, but there is a fair amount of overhead with FPGAs. So that's why, if my FPGA chip is this big, it's never really that big, but if I was to make an ASIC chip, it'd probably be that, okay? So FPGAs are awesome for launching products early. I can reprogram this giant chip, but it's a big waste of transistor. So then you would go off and make an ASIC chip, okay? FPGAs are like something like $5 billion per year of the market, but custom ASIC chips that are just like not sold to everybody, just for yourself, are something like $80 million. Okay, so as soon as it goes high volume, then you make the jump and say, we're going to go make mass so that we can make this small chip. Yes.
Is there like kind of tangible limit on time to reprogram FPGA?
No, it's fine. Well, if it's a flash-based, in theory, maybe 10,000 times, but most FPGAs are not flash-based. The bigger ones are not. You put the flash memory outside to store all those zeros and ones.
They deploy them to where like they kind of change based on what the load is that day, and they're like dynamically changing, so that should be very efficient.
They do that in data centers a little bit. They'll change the function quite a bit, but those are giant FPGAs that you can reprogram as many times as you want. It's the floating gate has a wear out mechanism. This is just kind of you take a bunch of lookup tables, maybe this is an 8 input instead of 4, you add adders, and you replicate these into larger functions, and then you stamp them out all over your chip, and then you have interconnect fabric, what we call it. It's how to connect them all together. And then the interconnect fabric, again, if I want to connect this to this in an ASIC, I take a vertical wire, a horizontal wire, and I put a via there. But for FPGA, because it's flexible, I got transistors all over the place, right? So I got these what are called pass gates, and then these are usually at least 6 transistors. So 36 for the SRAM, so 42 transistors in an FPGA, and just a piece of metal for an ASIC. Okay, but super flexible, right? So that's how it's all connected in the layout. And then you build, this is the type of chip we're going to use in today's lab. This is called our Cyclone 5 SoC. Besides all the lookup tables here, DSP and multipliers here, you got memory here, you got ARM, processor in there, you can run embedded Linux and all sorts of cool stuff for embedded projects. High-speed I/O, that's what what's called a transceiver. So most things like Ethernet, PCI Express, USB, HDMI, other DVI, other video interfaces, you name it, they're using these high-speed things. These take a little bit to explain how they work. I don't know if they study it. This is the thing I always feel like you should study in undergrad, how these things work, but most people don't. And I don't have the time to explain it right now, but if you ever get a chance to read up on how transceivers, that might be a good thing to have in your toolbox to help with your interviewing. All right, now that's hardware. Now talk about software. Most of it's going to be Verilog PCM. You guys use Verilog here, right? So I got a bunch of different ways to design an FPGA. Here's a Verilog. You should recognize that. Up top, it's C++. So you can compile C++ with some kind of additional, I don't know if you can see that far, but it says parallel 4. So you write C++ with no registers, there's no pipelining. It just goes and tries to like build it and figure out all the pipelining for you. It doesn't generally give you as an efficient implementation, but it's like 10 times as fast to develop your algorithm. Okay. You can also use that to just prototype or just go in and like simulate and try out your algorithm and then move it to an LTO later. No one uses schematics. They're fun to look at, not very fun to design. And then there's something called Platform Designer, which is all those IP blocks I had mentioned in the previous. That's the way to stitch them all together. if you get a chance to learn this tool from us or the Xilinx one, I would highly recommend that you learn how to use. This thing is called Platform Designer, and it's basically like a bus. And you plug things into the bus. You have, master screening and master memory, master and slave devices, and it connects them all together. Okay, so that's platforms. All right, so keep moving. Get you started on your lab. Talked about IP. Talked about Quartus a bit. Show of hands, who's used Quartus? About a third of you. You guys don't count. You pay to use Quartus. All right, so let me walk through Quartus. Who's used Visual Studio? Some of you Eclipse, some of you PyCharm. They all kind of have the same flow. Set up a project, add a bunch of files, hit compile. Hopefully you don't have syntax errors. And, if they do, start again, keep going, get rid of that part, then, try it out, see if it works, debug. Kind of the same thing with Quartus, but it's harder. Okay. What's a little different is the constraint. So constraints for this is like how many megahertz it's going to run or where the package balls are assigned on the printed circuit board. So in today's lab, you're going to write a little bit of Verilog, you're going to constrain your design, you're going to compile it. We're going to skip the timing part. Don't worry about that. You're going to program it on a board, and you're going to do it all virtually. Okay, so normally I'd come into places like this with a big suitcase full of boards, hand them out, get them back to you, from you, and find all the missing power supplies at the next university I do. But now we have this really cool virtual setup, so we're going to do it that. Okay. When you compile, you're going to get something called an SOF file, SRAM object file. And that's where you're going to use to program the chip. It's a volatile way of programming, which means when you power it off, it's going to lose its function. All right. Sorry for going so long. I'm trying to see if there's anything I can just kind of skip through. All right. So you're going to start with the new project wizard. You're going to give it a name. The lab manual is really good. We've run this lab a lot, and most people get through it pretty quick, especially with 3 of us walking around. So in the interest of, we got an hour 40. If you ask a lot of questions, you'll be able to get through these labs. I kind of want to just get to how we're going to program the FPGA. So if you've worked with Quartus before, this is the kind of like, you pick the file, you hit start, they ask you about how you want to connect to it. It says 100% success, and then you look at the board and go, okay, cool, it's working or it's busted. But we're going to use a virtual FPGA in this thing called LabsLab. And so kind of like this, there's a rack of boards with a camera on it. And there's this kind of web interface to allow you to program a virtual board. Okay, this board that you use today is probably going to be from University of Washington, Seattle. If everybody hits program at the same time, it might jump to another university. It's like it's all pooled and they schedule it all. But this company's been a great partner. It's just like a 2 or 3 person company that we do a lot of work with, that has all sorts of different labs that are virtualized. So you can check it out and you can see all the different type of stuff that they do. They have like Arduinos and robots, and you can even like blast radiation at things remotely and read all the gauges and stuff and see if you're, causing a nuclear meltdown in Australia or wherever it is that it's supposed to. That's a better view of how it's set up. So this one is a partner in Spain. These are the type of boards. This camera here. Okay, so you're going to program the board, and you're literally going to be looking at what the camera is seeing, and you can see the LEDs
value of the switches and stuff through. The Raspberry Pi is, kind of a mechanism.
I was like, change it, wired up like that, or is there like?
It's kind of a little trick that what they do is like when you say switch, they change the package ball on the constraint to not actually connect to the switch. They make it go to the connector to the Raspberry Pi. So see these ribbon cables here? So obviously I can't change the value of the switch without having a mechanical hand. So I just rewire a switch, it goes through the cables, and then there's a Raspberry Pi changing that. Yeah, it's kind of clever. Okay, so first lab, one line of Verilog code that does anything, assign the LED to the value of the switch. But this lab will probably take the longest because you got to do a bunch of setup to get to that. Then the second one's usually quick. It's just a multiplexer and just through the switches and LEDs. And the third one is what I affectionately call a blinky light demo, which is, you guys ever seen Knight Riders? Know the show? So in the beginning, there's kind of this, it's, if you've never seen the show, it was like in the 80s, really popular detective show with a self-driving car, and it had this light sequencer that goes back and forth in the film. So you're going to build that function. I give you most of the code, but some of it's busted, and you got to figure out what's wrong. And yeah, we have plenty of helpers. So again, I want to see a lot of hands going up just to get you moving quick. And if you want to get boards, I don't know, what boards do you guys use here, Jeff? Okay. Yeah, so this is a good board. If you ever want to buy a board, play around that Deep 10 Lite, you can finding them on the Terasic site. They're $73 now, and Amazon sells them, and they will get them overnight, but they're more expensive. He's got one there. Yeah. Yeah, and I might. The DE1 SoC that you're going to use remotely is like, it's like a $300 board or something. But it does all sorts of audio and video, and it's pretty. What is it? Yeah, that's because they're greedy. That's some reseller that's trying to capitalize on it. So I think that's it. So let me do this. Is everyone on the Zoom? Everyone connected to the Zoom, or if not, I can just write the GitHub link that you need to get the material. But you need to start by downloading a zip file, and then you'll just start going with it. Pardon? Okay, so let me just put it up on the board. I got a question on the chat because, okay. Just a moment. Sorry for yapping so long, but
If you want to work, you will need either a Windows or a Linux operating system from the labs, or a good buddy.
or a buddy.
You're not moving.
That's can you guys see the URL on this guy? Is that okay just to type that in? I can write it extra large. You need to go there and then grab that zip file.